you keep eating. That'll keep you from saying something to me.
He made me finish eating, but
I made him finish here. So I think most of you were at last night's talk. I'm not going to give the whole spiel about who Shane is, but just real quickly. He's Research Associate Professor of Physics at Northwestern University, where he's Associate Director of Sierra.
Oh, you got it.
I'm teachable. And he works in the field of gravitational wave astrophysics, etc. He's intimately involved with LIGO, which if you were there last night, you should now know what that is if you didn't catch the news 3.5 years ago anyway. So he's going to talk to us today about basically the start of the universe to Jackson Hole.
Jackson Hole.
So if that's not an all-encompassing topic, and more so than we've ever had before, I can't think of what it might have been. So without further ado, please join me in welcoming Shane Larson.
thanks everyone. So, when we were trying to figure out what I should talk about, we were kind of hemming and hawing and going around. So I just started sending titles, right? And the instant this title went through, it's like, yeah, that's the one we're going to listen to, right? So I was telling my table here at lunch earlier that for the last 3 years, my talk life has been dominated by the talk you heard last night. It's brand new astronomy, it's things that people are really interested in. So it's a treat to be able to give 2 talks, because I haven't really given any talks except the gravitational wave talk in a long time. But I do give a lot of other talks, and this is one that folks like to talk about. What's true about everything, the talk I gave you last night, the talk you're about to hear, is that we could have a conversation like this every day for a year and not talk about everything that we could possibly talk about. These subjects are vast, there's lots to discuss, lots to ask questions about, lots to ponder, and we know a lot more than I can tell you in an hour. So really all I'm doing last night and tonight is I'm going to tell you some stuff, things that I hope tell a coherent story, and there will be things that you've heard about that you may like to know more about. There will be things you haven't heard about. But the truth is we're just going to kind of go from the start to the end. And as we go along, if you have questions, as last night, those of you who were here, please ask. If they take us too far afield from the story, I'll hold them off till the end, and then we can talk much more then. But I'll try and answer them as we go along to kind of help keep us flowing. And at the end, we'll take as many questions as we want. If, by some chance, you have more questions, either tonight or 2 weeks from now, right? My email address is here, s.larson@northwestern.edu. It's there for a reason. It's for you to send me email that says, Larson, huh? Okay, and I'll try and send you the books. I'll send you the things to read. I'll answer your questions if I can. Kind of help you expand your understanding of this topic as much as you're interested in. Okay? There's a link there to my blog at Right Science. I have written about Big Bang cosmology there a few times. I've written about it in the context of gravitational waves as well. I know there were some questions about that last night. But if you're interested, there's a whole bunch of astronomy and other stuff there as well. And there's my social media contacts on Twitter and on YouTube. Okay, so tonight, really, I just want to talk to you about where does all the stuff around tonight, I guess it's today, I keep thinking about it tonight. Where did all of this stuff that is around us come from? The quest to understand the universe around us has largely been a quest to understand how everything that you can pick up is different than everything else. And the story I'm going to tell you is actually a very young one. We've asked this question for as long as we've had recorded history, but the understanding of what's going on, of how the universe is put together, and where all the building blocks came from, is something that we've only understood for less than a century. Okay, it began in the 1800s, but the understanding that we have today has really only come about since the 1920s. Okay? So, the biography of atoms is a story, and it begins with the birth of the universe. So that's where we'll start, although we won't start there. Midway through, we'll start there. And it ends with the lives of the stars. The lives of the stars lead to me and you, and those of you who grew up in the days of Carl Sagan, like I did, know that Carl said a great truth, which is we're all made of star stuff. Okay, and so this is why this is what the story is about. Everything that you see around you ultimately came from the stars. And what I want to do today is tell you the connective story of how it started and how it got to the stars before it got to me and you. Okay? Now, when I do this talk, I normally go out and find a rock. But in Jackson right now, I can't find any rocks. So you'll have to use the rocks that I did the last time I gave this talk when I was in Bozeman. Okay, so these are 2 rocks I just picked up off the ground in Bozeman. They're probably not dissimilar from the rocks you can find here in Jackson. Okay? Now, if you're a scientist, this is especially true of astronomers. It's very true of biologists. It's probably true of geologists. I don't know. But all science begins with what we call taxonomy. It begins by picking up objects and looking at them and simply describing what their properties are based on what you can see. Okay? And when you pick up 2 rocks, they're both rocks, but they look different. They're clearly not the same. And if I look at them and I began to delve into this taxonomic classification, I would look at things like their shape, their size, their color, their hardness, okay? Ultimately, their composition. They certainly look like they're composed differently, although the microscopic composition is a different story, okay? But these are the things that tell you how these 2 rocks are different than each other. And ultimately, these are the exact same things that tell me that a rock is different than you, or different than a frog, or different than a pine tree, or different than the snow. The things you can see with your eyes clearly tell you that the universe is constructed in very complex ways. And what we'd like to understand as scientists is, well, where does that complexity come from? And is it possible to disentangle that complexity to tell you why a rock is different than a tree or a frog or you? Okay? And so ultimately, to get at that question, we ask this question right here. What are the rocks made of? If I could go down to the fundamental building block of anything, rocks in this case, what are they made of? And so the way I like to think about that is I like to think about pie, because I like pie. Okay, so I like cherry pie. If I take a cherry pie and I cut it in half, what happens? Yeah, I get bigger because I eat half of it, and the pie that's left gets smaller. Okay? Now, how many times can I cut that cherry pie in half, cut the pie in half, cut the half a pie in half, cut the quarter pie in half? How many times can I cut a piece in half before I get to the fundamental building block?
A mathematician would say infinity.
well, it is turtles all the way down. Okay, but let's go to the level of atoms. That's what we're after. Yeah. Okay. Guesses?
100. No.
100?
No.
Okay.
A billion.
If your buck knife's really sharp, 100?
A billion.
A billion?
Yeah, 10 to the 10th.
10 to the 10th.
10 to the 10th.
Okay. 40.
That's all?
Only 40. Now that is astonishing because the number 40 is a very small finite number. But if we break a piece of pie down, cutting it in half only 40 times, it gets down to the fundamental thing that you build a piece of pie out of.
Really?
And your eye can't see it, which is the other astonishing bit. Okay? Now this is an ancient idea. The Greeks actually thought of this. They couldn't do it, but this is the way they thought about atoms. So if you study Greek philosophy, this group of people, they were called the atomists. They believed that the universe was built out of fundamental building blocks that you could get to by cutting things in half. Okay? Now, these small bits that we're talking about, there are smaller bits, as we said here at the front table. We'll talk about those later, okay? But everything is made of these atoms, whatever they are. Whether it's you, or the cherry pie, or the rock, or the frog, or the pine tree, or whatever, okay? But if I look at my rock or my piece of cherry pie, it's clear that they're different. And so there's something secret and weird and startling hiding in the statement that they're both made of atoms. Because they're clearly different. They're not made of the same atoms, per se. Otherwise, I could eat a rock the way I'd eat a piece of cherry pie. Okay? So the point is that even though they're built out of the same building blocks, the building blocks are put together in different proportions and different combinations which make a rock, and a cherry pie. And that's what the story of trying to understand what the universe is built of is all about. Understanding how the building blocks make a rock, and make a cherry pie. And the startling discovery that we made, starting in the 1800s and culminating in the 1900s, is that there are only 92 naturally occurring building blocks from which everything that you have ever seen, or ever picked up, or ever held, are made out of. And we call those the atomic elements. They're the things on the periodic table that you learned about in chemistry. There's only 92 of them, but with 92 of them, you can build everything that we've ever seen. Frogs, structure, yeah, everything comes from those 92. Okay? So once you realize that, you begin to ask yourself the other piece of the question. Okay, what are the proportions and what are the combinations? How do I take those 92 elements and make cherry pie versus rocks? Okay, and so the way you do that is you pick up objects and you look at them. So I'm going to go through a series of objects here because this is getting at the heart of what we as astronomers worry about. Let's imagine ordinary earthly organisms, okay? Plants, animals, anything like that. Okay, you have to pick an organism. I often pick kangaroos because I like kangaroos. When I give this talk to kids, they like foxes, okay? But since I'm in the West and I'm home, I like yellow-bellied marmots. Okay? So if I take a yellow-bellied marmot, it's really no different than if I picked you, but let's pick a marmot. Okay, if I just took 10,000 atoms out of that marmot and sorted them into piles of those 92 known elements, what do I get? There's about 6,500 oxygen, 1,800 carbon, 1,000 hydrogen, 300 nitrogen, 150 calcium, 100 phosphorus, potassium, sulfur, chlorine, on down the line. By and large, the atoms that have familiar names are the most common ones that you encounter in the world around you. Oxygen, carbon, hydrogen. Things down at the bottom, sulfur, potassium, phosphorus, they're things you and I have heard of, but they're not as common as the other things because they're in less proportion when you start looking at the things around you. Now this proportion, I take any 10,000 atoms from my marmot, from his ear, from his paws, from his fur, I'll get roughly the same amount. And it's true if I take a pine tree, it's true if I take a person, it's true if I take a frog. For living organisms on Earth, these are the rough proportions. Okay? There's a hand. Yes, sir?
How many atoms total would be in a yellow-bellied marmot?
Oh, boy, I should know the answer to that. I can figure that out, I don't know off the top of my head, but a lot. It is, let's see here.
2 times 10 to the 23.
Yeah, there you go. Yeah, so
Avogadro's
number.
10 to 23 times.
Times its weight in grams.
Its weight in grams. And so how much does a marmot weigh? I know.
That one?
5,000. That one. That's a fat one.
That one.
Yeah. So 10 to the 30, something like that. So.
It might be distorted by pine nuts.
Okay. So if I can do this for the yellow-bellied marmot, I can do it for the rock too. Okay. So if I pick up my rock and I just take 10,000 atoms from the rock, I also get atoms that I'm familiar with, but in different proportions. Okay? I get mostly oxygen, 4,600 of them. I get silicon, lots of silicon, right? The Earth is made of silicates, right? Aluminum, iron, calcium, sodium, magnesium, potassium, titanium, hydrogen, and other stuff, depending on which rocks you pick.
Interesting, but hydrogen is way down the bottom.
Hydrogen is way down there.
Huh.
Yeah. Okay. Well, because most rocks are hydrated, right?
That's right.
Right. Most rocks, that's right. Right? We're taking the average, right? The average rock on the Earth's crust, not the cool rocks all of you pick up and put on your shelves at home. Okay. Okay. Now, let's think about the universe, though, right? Our scientific investigations of the universe begin here on Earth. And it's natural to start with marmots and rocks. But the universe isn't, so far as we know, full of marmots, right? There are planets elsewhere, we'll talk about that in a moment, but there aren't very many planets. Really, the universe is made up of stars. Okay? So, let's look at the star closest to us. That's the sun. If I were to take 10,000 atoms from the sun what would the composition be?
Hydrogen, helium.
Yeah. 9,000 of them are going to be hydrogen, more than 90%. A little bit of helium, even less of oxygen, even less of carbon, less of neon, nitrogen, and even less of everything else. The sun is not an abnormal star. It is much like most stars in the Milky Way. There are stars that are very different, but they are not the norm. The sun is the norm. And when I look at other stars, this is what they look like. So if stars are what make up the cosmos, then this is what the proportion of those 92 elements in the cosmos is close to. The universe is mostly made of hydrogen.
I'm surprised the neon. I would have expected argon because it's so much more plentiful in our world.
Yeah, it's all about the history of the stars that led to the sun, right? So the sun's in the process right now where it's only fusing to helium, and so the contaminants in it are from the generation of stars that came before it. And there's a neon sequence in the burning sequence, and we don't know where the sun came from. We would like to. If you want to write a PhD thesis, I got a project for you.
Amazon.
Okay? So this is what we're after. We want to know if the universe is mostly hydrogen, where did it come from? And where did all of the other stuff, which is in far less proportion, come from at all? Okay? So the story there, so this is where I'm going to jump all the way back to the beginning. The story there is really about how all of this came to be in the universe. Okay? And the understanding of that began in 1929. So Humason and Hubble were the first people in 1929 to understand that the universe was in fact expanding. This had been predicted theoretically some years before by a Belgian priest named Georges Lemaitre. He had predicted that this would be true based on our understanding of gravity at the time, and everyone kind of ignored him. Okay? But then Hubble and Humason discovered, oh, the universe is expanding, and now we call this we use Lemaitre's name to describe this expansion, the Lemaitre equations, yes. So if the universe is expanding, that kind of really redefined the way we think about the universe. And in particular, what we do as astronomers is we say, okay, if we see it doing this today, we see it expanding, what does that mean the universe was like yesterday? Okay? And those of you who've heard astronomy talks before know that looking back through the universe is looking back in time, because it takes enormous amounts of time for the light from the distant universe to get to us. And as we look back through the universe, what we see galaxies in their earlier stages of life, and we ultimately will see the first stars, and beyond that, we don't know. But we can predict what would happen. And what we think happens is as the universe goes back in time, if it's expanding now, it was smaller in the past, because it was smaller and got bigger. And what we know is when you make things small, they get hot and they get dense. And when things get hot and dense, it breaks things up, mashes things together. And so things that you and I are familiar with today, in particular stars and atoms and the things that they're built of, disintegrate. But we're moving forward in time. So the story of the universe's evolution is how do you take a pile of stuff and build atoms? Whereas the way we normally describe it is as I go backward in time, I squish the atoms and they disintegrate because I'm looking backward in time with my telescopes. But let's tell the story forward in time. Okay, so we're not going to talk about the beginning. Okay, the laws of physics have nothing to say about the beginning. They don't work. They break down. We have to start 10 to the minus 43 seconds after the beginning. Okay?
You're almost there.
Yeah, well, it's still a long ways. Okay? So 10 to the minus 43 seconds after the beginning, I can tell you what was going on. Okay? So, the universe was small and hot. Okay? So, I have to tell you some basic physics. How many of you loved physics when you were in school? Okay, a few of you. Okay. So here's all the physics you need to know to understand the story today. Okay. So, when things are hot, they move fast. And when things are cold, they move slow. Okay? And then, when things collide, if they're moving slow, they stick together. And if they're moving fast, they break apart. Okay? So that's the only physics you need to know today.
Where were you in high school?
I got a spot in my physics class for you right now. Okay? Okay. So this is what we're going to talk about. Okay? So when it's hot, you're moving fast and you can't stick together. When it's cold, you move slow and you can't stick together. Okay? So when the cosmos was young, 10 to the minus 43 seconds, it was hot. How hot? It was 10 to the 32 degrees centigrade. That's 100 million trillion degrees. When I give this talk to kids, I'm like, count to 1 trillion. Do that 1 trillion times, and then do that 100 million times. I'll wait. Okay? It's a huge number. Right? It's all those zeros, okay? And we write it this way, 10 with the 32, the 1 followed by 32 zeros. That's really hot. It's so hot that you and I can't experimentally do that in any laboratory. We're trying in the LHC, but we can't quite get that hot. Okay? So, when you're at those temperatures, atoms can't stick together. They're hot, they're moving fast. When they're moving fast and they collide, they break apart. Okay? So, there were no atoms in the beginning. So what were there?
Energy.
Well, there was stuff. The cosmos was filled with the building blocks of atoms at this point. Okay? So things that you and I call protons, neutrons, electrons, and energy in the form of light. It's a great mystery where all the light came from and why there is as much light as there is. That's another long story, but if someone wants to talk about it, I can tell you at the end. Okay? So,
Question.
this, yes.
Okay, so we got matter up there, protons, neutrons, and electrons, if you want to call electrons matter. What order did they appear in, and how cold did it have to get until a proton could become a particle?
So I've skipped over that, okay? Because protons and neutrons can be broken into smaller particles called quarks, okay? And the story I'm telling you right now about the formation of atoms, I can also tell you about the formation of these, which are called nucleons. Okay, and I don't know those numbers off the top of my head because I didn't put them in the talk. But there's the exact story I'm telling you now.
But there's a precursor to...
There's a precursor to
matter.
these.
Yeah.
That's right. Well, but quarks are matter.
Yeah.
And so then the question is where did the quarks come from?
Some say they don't matter.
Well, you've been talking to mainstream theorists. Okay. Did I say that out loud?
Yes.
Okay, so we call this the primordial soup.
Yeah.
Okay, and what we mean by primordial soup is this. Okay, it's just all there mixed together. Okay, and when protons get close to other protons or close to neutrons, they don't want to stay together because they're moving so fast they bounce each other and just go on their way. Same with the electrons, same with the light. Okay, it's just a morass of stuff. Okay, so the universe continues to age. And as it continues to age, it expands. Okay, and the key point in expansion is that as you expand, you're taking all of that pent-up energy and heat and smearing it out over a much larger area. Like when you have a stack of mashed potatoes or scrambled eggs on your plate, you spread them out and they cool off. That's what the universe is going to do. Okay? So, the universe is cooling off, and if I wait 100 seconds after the Big Bang, how cool is it going to get? It'll get down to 10 billion degrees centigrade.
Ratio of the time.
Okay? That is a temperature we can get to in the laboratory. Okay?
Really?
Yeah.
Yep.
That's what we're doing in the LHC right now, for instance. Yeah. Okay? 10 billion degrees centigrade. It's still hotter than any normal temperature on Earth. It's still hotter than the core of the sun. Okay? But we can get to these temperatures. Okay? And at 10 billion degrees centigrade, protons and neutrons can stick together when they hit. They're now cooler than they were. They're not 100 million trillion degrees. They're now only 10 billion degrees centigrade. So now when they hit, they can stick together. As we say, the nuclear forces can bind them together. Nature is comprised of forces. Forces are like little hooks. And when you hit each other, if you're going slow enough, the hooks can grab on. And so that's what happens at this point. And so this point, 100 seconds after the Big Bang, all of these nucleons, protons and neutrons, stick together, and we have a name for that. We call it nucleosynthesis. The synthesization of all the nuclei, the cores of the atoms. Okay? So that's 100 seconds. Okay. When's the next most important time in the universe?
About a year.
Yeah, the universe is really boring now for about 400,000 years. So 400,000 years after that, the universe will finally cool to about 3,000 degrees centigrade.
No question. Did any of the pieces not form an atom and just...
Yeah. So we will come back to this, but hydrogen is a proton without anything else.
Okay.
Okay. So when nucleosynthesis happened, the smallest nuclei were created. Proton plus a neutron is something we call deuterium, heavy hydrogen. Helium forms, lithium forms, and not much else. But the lightest stuff forms at that point. But still, most of it is just protons. It's just hydrogen.
Right.
Okay? Yeah. Okay? Other questions? Okay. Now, 3,000 degrees is an awesome temperature because you and I can make 3,000 degrees in our backyard. You can go home and do cosmology experiments in your backyard. Some of you do. Have any potters with kilns in their backyards? No? No? Okay. Well, if you have welders, a few welders, any welders out here? Okay. You have the makings of cosmological experiments in your backyard. Okay. After 400,000 years, the universe continues to cool. And what we mean by that is the energy is getting more dispersed, the atoms themselves are starting to move slower, and so when they move slower and they collide with each other, they don't always break apart. And in particular, when you reach these temperatures, then when electrons hit these nucleons, protons, or combinations of protons and neutrons, they can stick. And that's the last building block in what you and I were taught makes up atoms. Atoms are protons, neutrons, and electrons. So at this point, when I reach 3,000 degrees, we finally have atoms. Now, I'm telling you the story forward in time. But I told you that physicists think about this story backward in time. So the name for this event is a weird name. We call this recombination. As if these things used to be together and then were broken apart and then are put back together again. So it's like this is how astronomy is. You all get used to this. But this is actually combination. This is the first time in the history of the cosmos that electrons and protons and neutrons combine to form atoms. But physicists call it recombination. Okay? Okay. So, if I at this point took 1,000,000 atoms out of the soup of the universe that had combined from the protons, electrons, and neutrons, I would get 1 lithium, about 100,000 helium, about 1,000,000 deuterium, and that shouldn't be 1,000,000. Sorry, 1,000,000,000.
Yeah.
Sorry, I took 1,000,000,000 atoms. Okay, then I get 1,000,000 deuterium and 998 million hydrogen atoms. Okay, so already here, in the 400,000 years after the Big Bang, you can see what our observations of the nearby modern local universe tell us, which is mostly the universe is full of hydrogen. That started early on. And in all likelihood, lots of the hydrogen that you encounter today in your everyday life started here. Hydrogen it does get reprocessed, it is formed by other atoms, but the propensity of it in the cosmos means that most of the hydrogen you encounter is from the earliest moments in the universe. Which is kind of cool. Okay? Okay. So what happens when I make atoms? Okay? These are great things to work out. I'm a theoretician. I can work this all out on paper and tell you this is what we think happens based on the laws of physics. But as an observational astronomer, I'm like, okay, that's a good story, but let me go look for something to convince myself that this is what happened. Right? Science is both cool ideas and observations that confirm your cool ideas. And as astronomers, this is what our whole game is about. And so I would like to look for the signature of recombination. And as it turns out, I can see it. Before recombination happened, all of those nuclei were floating around, all the electrons were floating around, and light was floating around. It was still a soup, although not the primordial soup. And when you have charged particles, electrons and protons flying free, and you have light mixed in with them, light doesn't like to walk by an electron and not talk to it. Okay? So as light's cruising around, if it sees an electron, it bounces off the electron and starts traveling in a new direction. The electron also bounces and goes in some direction. If light's traveling along and it sees a charged particle, it bounces off of it and changes some direction, and the particle goes in some direction. It's a lot like when we're all hanging out in a big party, we're all talking and laughing, and I got to get over there to the punch bowl. I can't walk in a straight line. I got to stop and talk to John, and then I kind of weave my way around Jennifer, and I go in this kind of random walk. And this is what all the light in the universe was doing, because every time it sees a charged particle, it got to stop and talk to it. But when I make atoms, the fundamental property of atoms is it's neutral. It has just as many protons as it has electrons. And so when the light's flying by, it doesn't see any charge anymore. And so suddenly, the light can travel in straight lines. So we call that decoupling. The light is not coupled, it's not talking to the electrons anymore. And today, we see that light as the cosmic microwave background.
Why is the light attracted to a charged particle?
The interaction between light and charged particles is that light is the fundamental communicator of the electromagnetic force. Light is an electromagnetic wave.
True.
And it is generated by moving charges, and charges themselves interact with light when it impacts them.
Okay.
Now, why, right, you could be the 4-year-old about that and say why, but why is a harder question. But light is the fundamental interaction in electromagnetism.
You're right here. You're kind of showing light as a particle as opposed to wave.
Yes, absolutely. Yeah.
Yeah.
Yeah, we're ignoring that wave stuff.
Okay.
Yeah. Okay. Okay? Okay. Other questions? Okay. So, this was predicted in the 40s, I guess. And there was a concerted effort to look for it, largely by the group at Princeton. Those of you who know anything about the cosmological history, Dickey and his group at Princeton were looking for the cosmic microwave background, but it was stumbled on by Penzias and Wilson, who were microwave engineers at Bell Labs, who were trying to make phones sound better. Okay, and they discovered the cosmic microwave background, but what we discovered is that the cosmic microwave background is coming from every direction in the sky at roughly the same strength. This is the signature of the birth of atoms. This is the signature that the universe was once much hotter and denser than it is today, and that when it cooled, atoms formed and left us the microwave background light as the signpost that said when that happened. The cosmic microwave background is the most distant thing you can see in the universe. You can't see anything past it because it blocks everything from behind it, with the exception of gravitational waves, which we talked about last night. Okay? But there is no light that comes to us from before the cosmic microwave background. You okay?
Yeah.
Okay.
What is there anything behind?
Yeah, there's the primordial soups behind it.
Oh, okay. Soup.
But the light's all tangled up, and it's hitting, and it can't get to you. This is the point where the light suddenly says, I can travel in a straight line from where I am now to you on Earth. That's why you can't see past it.
So we think some of the soup is still back there?
This is the... Yes, If I could see through the microwave background, I would see the soup. Is it still there? Well, what do you mean still there? Right? Looking across the universe is looking back in time.
Yeah.
So that place in the
yeah.
universe is evolving just like, right?
Oh,
There's astronomers there looking towards Earth, and they see the cosmic microwave background. And there's some astronomer there asking, is the soup still there? And the person talking to that astronomer is saying, yeah, that soup has evolved into people who are standing behind the microwave background talking to you, right? Okay.
Gotcha.
Cosmology is hard, right? This is not easy stuff, y'all, right? It melts your brain. Okay? And one of the things that we struggle with in cosmology is when you study cosmology, you have to come to grips with questions like this. And what we mean by come to grips with is you have to become very diligent about asking very precise questions which can be answered. And not worry about the philosophical implications, unless that's what you want to do. Okay? And then it requires lots of pizza and beer. Okay? Okay, so this is the signature of the formation of atoms. And the question is, how did we get from them to us? Okay. So, 400 million years after that, we think stars should have begun to form. We are looking for the light from the first stars. We still have not seen it. The James Webb Space Telescope, which is a successor to Hubble, this is one of its #1 science priorities, is to detect the first light from the first stars.
Yes.
Yes, right? Because we would like to know, is this right? Is this when stars first formed? And there's a whole host of questions that go along with that. Do stars come before galaxies? Galaxies come before stars? What role does dark matter play in all of this? Right? There's a long list of questions that we would like to answer. But it begins with detecting the light from the first stars. Okay? But we can learn a lot about the formation of stars by looking at the universe around us. Because we see stars being born right here, close to home, in the modern universe. Okay, and that's how we've gotten to this story that we're all star stuff. Not by detecting the first stars, but by looking at stars around us today. Okay? So, this is a very famous star formation region, which you can see, we saw it last night actually, when the clouds part. If you look towards the constellation of Orion, you'll see his 3 belt stars, and hanging from his belt stars are 3 stars that we call the sword, but the middle star is not a star at all. It's this object. It's called the Orion Nebula. If you have a pair of binoculars and you look through binoculars, it won't look this colorful, but it will look like a cloud like this. Okay? This is a stellar nursery. There are stars being born out of this vast cloud of gas in the galaxy. And if we look at these stellar nurseries, we can see that process of star formation. Okay? Stellar nurseries give birth to what we call clusters. So this is a very famous cluster you can see in the spring sky. This is called the wild duck cluster. So if you have amateur astronomer friends, they can show this to you in binoculars or a telescope. I don't know why it's called the wild duck cluster. It doesn't look like ducks to me. My wife calls this crushed ice. She thinks it looks like crushed ice. It's a very beautiful cluster. It's great to look at. Okay? But when things like the Orion Nebula, it's forming stars here in the center. When all of this gas is used up and forms stars, the young stars blow away the gas and dust, and it leaves what we call an open cluster, a group of stars that are very young, just beginning their lives. The sun began this way. And one of the great quests of astronomers today is to find the siblings of the sun. Because these stars, when they're born, over time, they drift apart into the galaxy and go lead their lives, just like all of us do. How many of you were born in Jackson? Right. Okay? Same thing with stars. They're born together, but then they disperse out into the galaxy. Okay? You can see these with small telescopes and binoculars, so even if you're not an amateur astronomer, the binoculars you got for looking at elk and birds and stuff, you can see this sort of stuff really easily, and there's good guidebooks to help you see that sort of stuff. Okay? But let's talk about the stars once they're born, because that's where our story's leading. Okay? So stars spend most of their life in astronomer speak on the main sequence. Okay? So what do we mean by that? We mean stars are like people. They have a job. And every day they get up and they do their job, and they do the same job every day. And a star's job, when it's on the main sequence, is to get up in the morning and turn hydrogen into helium. And then the next morning, it gets up and it turns hydrogen into helium. And then it gets up and it turns hydrogen into helium. Over and over and over again for millions or billions of years, depending on how big the star is. This is what stars do. Deep down in the core, all of that hydrogen is being compressed together at such temperatures that when they collide, the hydrogen atoms stick together and they make different atoms. That same story we told about at the beginning when we were talking about the formation of the first atoms, the first nuclei in the Big Bang. It's happening in the cores of the stars again. Okay? So this is a movie showing this. Okay? They collide. When they collide, they release energy and some other particles called neutrinos. Okay? That energy eventually works its way to the surface, and that's what you and I see as the light from the stars or the light from the sun. But it goes through a process. Those of you who are physics nerds, this is called the PP chain. Okay? The PP chain starts with hydrogen, and you end with some hydrogen and helium. Okay? And this has been going on in the sun now for about 5 billion years.
So where are the neutrons coming from?
So you saw those neutrinos and particles going off. So neutrons are created in this process from protons. Okay? So, yeah. So the nuclear processes turn the nucleons into each other by absorbing or releasing electrons. Okay? So that process is called beta decay or inverse beta decay, depending on which way you're going. Okay?
In these star nurseries, are these imbecile stars getting larger? And once they reach a certain size, they go migrating off to somewhere else?
Yeah, so this is a big question, which is, if I just give you a stellar nursery, how many stars do you get, and in what different sizes do you get them? Okay, and so this is something we study in my group, actually. What tends to happen is you get a few big stars, more stars at kind of medium weight, and then a lot of little tiny stars. And that has to do with when you can imagine, if you break a cloud up, and say you can make 2 of the biggest stars you could make, there's some stuff left over. Well, you can't make a big star, so what can you make? Well, you can break it up and make some medium-sized stars. And then there's some stuff left over. What can you make? Well, you can't make medium-sized stars, so you make small stars. So that kind of, we call it fragmentation, is how you make stars. But it tends to make more smaller stars than bigger stars.
Because I thought I had read years ago that the sun was actually getting smaller. But if it's like this, wouldn't it be getting larger?
Yeah, so the size and the mass are 2 different things. Okay. So the mass is fixed at this point. It's giving off particles, but overall the sun's mass is fixed. Its size will change over time, depending on what's going on with this nuclear process down in the core. So right now, I don't know what it's doing right now, but eventually it will swell up. It'll become what we call a red giant. It'll expand out to the orbit of Venus or Earth, and then it'll shrink down again. But that's all a function of what's going on down in the core. Okay? Okay.
Now back to the stellar nursery, and what's making them drift apart is dark energy, or
they all, when they're born, they have some velocity that they're moving with, and there's not enough strength in the cluster to keep them all together.
the gravity's not okay.
That's the defining character of these birthing clusters.
Okay.
Is they don't stay together. Yeah. Okay. Anyone else? Okay. Okay? So eventually, when the sun gets near the end of its life, it will start banging helium atoms together, and it'll make carbon. And if stars are heavier, they can bang carbon together, and they'll make even heavier atoms. That's where the neon and stuff that we're talking about comes in. And it can make these heavier atoms all the way up to some maximum sized atom possible. Okay, so what is that? Okay, does this look familiar?
Iron.
Yeah, this is the periodic table. This was worked on in the late 1800s, but its final form was, I guess, around the turn of the century. Mendeleev, I guess, did it. But this is our organization of all of these 92 building blocks that we've discovered. Okay? And we can make all of these things in stars. I tend to look at it this way. This is what all of these things look like in their raw form, except this one. I guess that is raw xenon, but okay. So here's carbon. So stars like the sun will make everything in the periodic table up to carbon. Heavier stars will get all the way up the periodic table to iron. Okay, by this fusion process, this banging stuff together down in the core. But that leaves all of this, all of these 92, all the rest of the 92 building blocks in the periodic table. And the question is, how do we make all of that other stuff? The fusion processes in the core of the star cannot bang iron atoms together hard enough to make them stick. So to make all of this other stuff, you have to bang them together harder. So how do you do that?
Hit them harder.
You hit them harder, right? You blow up the star. Okay? The sun's not going to blow up. That's why it's going to stop at carbon. The sun will eventually throw off its atmosphere. It'll make a very pretty nebula, not unlike this one. Okay? And the sun will shrink down to a little core, a husk of what it used to be. A white dwarf. It'll be about the size of the Earth. It'll be largely comprised of crystalline carbon. What do we call crystalline carbon? Diamonds.
It'll still be radiating energy, right?
It will be cooling. It won't be fusing. It'll be hot and cooling.
Cooling off radiating
Like
residual.
your stove element.
Is the fusion of iron not possible in our sun? Well, is the energy coming out of a fusion of two iron atoms lower than the energy required to fuse them? In other words, there's no net release of positive.
That's why you can't fuse iron.
fuse,
Yeah,
yeah,
that's right. Yeah. It's energetically
costs you
unfavorable.
more to fuse
It costs more energy than you get out.
Then you get out.
Yeah. We can fuse hydrogen, but you have to invest energy. Yeah. Okay. Okay?
Could
So
you
the-
repeat the question, please?
So the question is, why can't you bang two iron atoms together and make them stick? And the reason is that processes like what I just told you release energy because nature thinks it's more favorable for them to stick together and throw that energy off than to remain separate. But for iron to stick together, you have to put tremendous amounts of energy in, more energy than you'll get out. And so nature doesn't like that because it doesn't want to use up all that extra energy just to bind these two iron atoms together. Okay? So that can't happen in a star. There's not enough energy to make it happen. At least not in this fusion process that we're talking about. Yeah. Okay? Does that make sense?
Yeah.
Okay. Everyone good? Okay. Okay. So carbon is where we're going to get with the sun, but there's all that other stuff. And you get to all that other stuff by blowing up stars. So if a star is 8 times the mass of the sun, when it reaches the end of its life, the fusion, the processes of banging these atoms together down in the core is going to stop. And when that stops, the gravity of the star says, ha
Here I go.
I'm going to take over, and it grabs everything that the star was and collapses it. Okay? Now you can go do experiments with this. You can go out, maybe wait till the snow's gone, stand on your roof. Okay? Drop things from 4 feet, drop things from 6 feet, drop things from 10 feet, drop things from your roof. And the farther it falls, the faster it's going, and the harder it will break when it hits the ground. This is the same thing with stars. Stars are very big, and when gravity takes over, things fall towards the core of the star. And they're moving enormously fast when that happens. And when all that stuff gets squeezed down to where it used to be fusing hydrogen, the star explodes.
What's the time element
Seconds.
of this? Seconds. Yeah.
Yeah.
Wow.
It just happens. Right? Now the fusion, that process, that balancing process, the fusion takes a while to turn off. But once the star's in free fall, the explosion proceeds very, very rapidly. Okay? Okay. These explosions are called supernovae. And the amount of energy they release in light is more energy in light than the sum of all the light from all the other stars in the galaxy. During the time the supernova goes off, this star, this explosion, outshines its parent galaxy. That's why there's energy to push the atoms together. All of that energy is available to synthesize all the heavy elements in the periodic table. Okay? It's 10 billion times brighter than the sun. There have been many of these. The last recorded supernova in the Milky Way occurred about 6 years before the invention of the telescope. There's not been a supernova in the Milky Way since the invention of the telescope. You want to see, we talked about how there were 4,000 astronomers on this paper, right? The first supernova in the Milky Way that happens in our lifetime, you're going to see a paper with more astronomers than you ever knew existed. Okay? Okay. But the most famous supernova is this one. So supernova 1054 was bright enough that you could see it during the day. You go out and it's like, oh yeah, look, there's the supernova. You can imagine in 1054 you would probably freak out when you saw these things. Okay? You could read by it at night. That's how bright it was. Okay? And then it faded and disappeared. But when we invented telescopes, we went and looked in the sky where that supernova used to be. And we saw something. Does anyone know what we saw? A nebula. Do you know which one?
Crab.
The Crab Nebula. So this is what is there at that point where that supernova went off in the sky. It is the shattered remains of a star that blew itself to bits. And all of the stuff that this nebula is made out of is the stuff that the star used to be on. It's hydrogen, it's helium, and it's a whole bunch of those heavy elements. All that stuff on the periodic table. It was made when the star exploded. Yeah.
Is there a group of elements up to some weight that a particular supernova can generate, or does it generate?
Ooh, that's a
all of
good
them?
question. I don't know the answer to that.
Yeah.
I think the answer is it can generate all of them, just based on the energetics.
And minute qualities at the
Yeah,
at the heavy
but
end.
I don't know the full answer to that question.
What was the question?
The question is there a limit to which of the 92 elements you can make based on how energetic the supernova is? Yeah, and I think you can make them all, just because the supernovas uniformly are very strong, but I actually don't know the answer to that question.
What kind of temperature and duration are we talking about for a supernova explosion?
Well, this is also a new frontier in astrophysics because we're discovering supernovas are not as simple as we thought they were.
But the duration of luminosity might be weeks.
For
to
these
months.
for these kinds of supernovas, the luminosity will peak after a week, and the supernova will fade over the course of years.
Yeah.
Okay.
This
Yes,
is
sir.
an amateur question. How do you know what elements are in there? How can you detect those through light spectrum?
So it's spectral. It's all spectral signature. So so I have another talk. I don't think I have the slide in here. But if you take light from a star or the sun and you pass it through a prism, you'll get a rainbow.
Mm-hmm.
But if you can make the prism really, the rainbow really big so you can see it, you'll see there's missing lines, missing colors, dark lines in the spectrum. And those lines are unique fingerprints for every atom, kind of atom that are in the supernova remnant in this case, giving off light. And so we just go through and we map them and we say, okay, these are the hydrogen lines, these are the helium lines, here's the sodium lines, and we can just map it all out. Okay?
Shane, have there been any other elements discovered by looking at these supernovas other than what people here on Earth have?
So when the periodic table was laid down, when we figured out the structure of that table, there were gaps. And so we went looking and were able to fill in the gaps. I don't know if any were discovered from supernovas per se, but there is a very prominent element that was discovered in the stars, not on Earth, and that's helium. Helium was discovered in the sun before we ever found it on Earth. We knew to go look for it on Earth because we had seen it in the sun. So I don't know enough of the history of how we filled in the periodic table to know if they were discovered in supernovas. But the history of all the elemental discoveries, especially the heavy ones, is known, and you can look it up. So, There's a great book from Nat Geo and DK, I think, called The Elements, and they will tell you the story in that book. Okay, other questions? Okay, we're almost done here. Okay, so this is where all the elements heavier than iron are made. It gets thrown out into the universe, and we see these supernova remnants all over the Milky Way. Okay, this is a very famous one in Cygnus. This is called the Veil Nebula. It's part of a very large supernova remnant called the Cygnus Loop. Okay, from places like Jackson, if you got a big telescope, you can see all of this structure very easily. It's a gorgeous nebula to look at. Okay, but when all of this goes out into the universe, it goes into what we call the cosmic recycling. Stars like the sun are not the first stars that were born in the universe. Stars like the sun were born from the ashes of other stars. That's why it has things like neon and calcium and all of those things that we said we found in the sun when we took those 10,000 atoms out at the beginning. Okay, so all of this stuff, when a star explodes, either the way the sun's going to die, where it throws its nebula off, or through a supernova, all of that goes back into the cosmic recycling bin and into those clouds that the stellar nurseries are formed out of. And so stars today in our own galaxy are formed from the ashes of the stars of yesterday. And it's just this kind of constant recycling process. And so you'll hear astronomers talk about population 1, population 2, population 3 stars. Those are generations of stars that have existed over the course of the history of the cosmos. Slowly recycling what was older stars into the stars we see today and into things like me and you. Okay? So when stars form, this is brand new in just the last 10 years or so. We are now able to see that the stars, when they form, they're also forming their own planetary systems around them. Okay? And I just saw, at the AAS meeting, I was in Seattle, there's a movie that we have now showing protoplanets going around their parent star. It is the coolest movie ever. And I just showing this slide now, I should have gone to show it to you. But anyways, these atoms that go into the stars, they also go into these disks that form planets, okay? And as of today, there are 3,976 known planets in the universe. There are an additional 5,000 that are not confirmed, okay? So there are potentially 9,000 known planets. When I started giving this talk, when I was in graduate school, there were 9. Because Pluto's a planet, right, y'all? Right, okay. There were 9. Okay, but now there are 9,000. There are so many planets that we're confident that every star has planets.
Sure.
Okay, so, but this is the process that we go through. Okay. Okay, so what do planets do with atoms? Well, the planet's crust breaks up into rocks. Weather and water grinds those rocks into soil. Soil becomes grass. Grass gets eaten by cows. You make ice cream, and we eat ice cream, and it becomes us. We're star stuff. Okay. So let me tell you one last thing. One of the things that we've started doing in just the time I've been an astronomer is asking the question, how much light is there in the cosmos, and comparing it to how much gravity we see in the cosmos. This was started in the 1930s, and we discovered the existence of something called dark matter, which I told you all a little bit about last night. Okay, but in the late 1990s, we discovered that some 73% of the universe is out there and doesn't emit any light, but it emits gravity as well. Okay, so this picture here is the picture we use when we try to answer that question. Is the amount of light and the amount of gravity in the universe consistent with each other? And the answer is no. The amount of light is consistent with the amount of atoms, the amount of star stuff in the universe, which is only about 4% of the universe. Okay, the colored jelly beans you see in this jar. All the rest of it, we have no freaking idea what it is. Which is why we have jobs as astronomers. Okay, so I'm going to end there. We've been going for a while, so I'm sorry we've run so late. So this is one of my favorite quotes from Carl Sagan. This is actually from Cosmos in the third or fourth episode there. where he's commenting on the differences between astronomy and astrology. And his point is we have this kind of deep need to understand how we belong with the universe. And his point is that we are part of the universe. We're deeply connected to the universe in very strong and important ways. And this is the way I like to think about it. We're all collections of atoms, which are the universe trying to understand what all the other atoms in the universe are trying to do, right? So that's the way we put it all together. So, okay. As always, here's a few books to read about if you're interested in this stuff. The First 3 Minutes by Steven Weinberg. Steven won the Nobel Prize for some work in particle physics. He'll talk about that very early hot time in the universe. The Day We Found the Universe, I mentioned this to you last night. That's by Marshall Bartusiak. It tells about the discovery of the expansion of the universe and the story with Hubble and Humason and Einstein and Lemaitre. And then Wrinkles in Time is a book by George Smoot. George also won the Nobel Prize for the cosmic microwave background experiment, COBE. And so that's a book about the cosmic microwave background. If you're an amateur astronomer, this is my favorite book in the world down here on the lower left. It's called An Observer's Guide to Stellar Evolution by Mike Inglis. It's a fantastic book. It gives you a tour of the sky so that you can see stars in all their stages of evolution and understand how all this goes together, one piece to the next piece to the next piece. So it's really a fantastic book to kind of occupy your evenings if you like spending time out with the telescope. So, okay, I'm going to stop there. Thank you all so much for your time. I'm happy to take questions, and I know some of you have to go, so please do that, but I'll take questions as long as you want to chat.
I'd like to ask you a question about yourself.
About me?
Yes.
Okay.
You're obviously a fabulous teacher. By the way, thank you for both last night and today. You're a great teacher.
It's my pleasure.
What's the mix of your time between teaching and doing field work or lab work, whatever you call it?
So I'm a university professor, and depending on what kind of university you're at, the proportions of time are different. So I'm at a research university, where for physicists, we are supposed to split our time between teaching and research. And so our teaching is basically a course per quarter, and then research all the rest of your time. I also work in the summer on research, so I don't know how to put a percentage on it.
And what motivates you to come out and spend time with pilgrims like us?
So I am a very firm believer in the idea that one of my obligations as a professional scientist is to go back and talk to everyone about science and why it's a necessary part of our lives. I grew up in a little logging town in eastern Oregon called La Grande, about 10,000 people, completely dominated by Boise Cascade. And I had never in my life met a physicist or an astronomer, but I became one. And so it's good to go back and talk to those rural communities that came from to say, this is all connected to us. I like groups like this because one of the things that I'm very adamant about is that the world in science and technology is changing rapidly. And the truth is, most of us haven't been in a classroom in decades. And so you're subject to learning this on your own, or having folks come out and have me talk to you like you're sitting in my class. So,
thank you.
that's why I do it. Yeah.
Thank you.
Okay. I don't know who was first, but yeah. Okay. Someone go. Okay.
I have a question to help me, because I'm a little bit confused from last night. You had one slide where the gravitational waves, where the two, they were created by the two, neutron something.
Neutron stars.
Then you had a gap, and then you had, I thought it was all black holes up there. And you said that gap, you had not found black holes nor the neutron. But that the latest one that happened in 2017, you thought was up there.
Yep. First one.
Okay. Tell me in relationship that is with this nursery of stars.
Yeah.
I'm confused in that.
Yeah.
I'm sorry because I don't know anything about
So
stars.
in stellar nurseries, the biggest star you can make in the modern universe is only about 35 times the mass of the sun. Okay? The lightest star is about 0.7 times the mass of the sun. Okay, so we can see stars anywhere in that range. Okay, the mass gap, though, isn't about stars. It's about the skeletons of stars. It's about what do stars become when they die. And when they die, they become one of three things. Black holes, the neutron stars, or the white dwarfs that I just told you about here. And if I just look at the neutron stars and the black holes, we've never seen one that's between 2 and 5 solar masses. And we don't know why. And we would like to understand that. Okay?
Clears that up.
Okay. Yes, sir.
Yeah, a little bit following up what my wife asked, but for heavy elements, so you're far above the endothermic nuclear binding energy of iron nickel.
Yeah.
So,
In fact, nickel's the peak. It's weird that iron's the
nickel is
limit,
the peak,
right?
right.
Yeah.
In spectrographs, I've seen tungsten at least, which is a very heavy element. But
In
the
stars?
question, no,
Oh, okay. Yeah.
from supernova.
Yeah. In supernovas, yes.
The question really is, you said that you can get all these heavy elements. I agree with you, but if you look at the total mass, the total concentration of heavy elements in the known universe, you're not going to get those. You're not going to get anywhere close to that from supernova. You really have to have the nuclear star collisions to generate.
Yeah,
enormous-
so this is something I've glossed over here, which
Okay,
is
so
the
I just
neutron
wanted
star
to make
event
sure.
from last night
Yeah,
that we talked about.
Yeah.
This is now part of this story.
right.
Yeah.
Okay.
Yeah. Okay.
Fine.
Okay.
Thanks.
So, and if you go to our papers, we wrote a paper about exactly this, but I glossed over that part of the story. Yeah, you're absolutely right. You need neutron star collisions to get to the
Yep.
to the limits. Yeah.
Right. Thanks.
Okay.
Is there a way to study or observe the age of a star or be able to determine when they might collapse? Will there be a cluster of them sometime in the future, or will they continue to be?
Yeah, so we work. So this is something called stellar chronometry. I think is the name we use for this. Is how do you figure out the age of a star? And it's very imprecise at the moment because there are no hard and fast rules. Okay, so I often liken this to, let's imagine I wanted to guess the age of everyone in this room. Okay, so we could do that. We could probably get pretty close because we've met a lot of people and we know what to look for, right? And we know what signs mean you're older and what signs mean you're younger, and some signs are maybe an indicator, maybe not. Stars are exactly the same way. So we look at their temperature and their size. Their temperature is related to their color, so we look at their color. We look at their rotation rates and the amounts of winds they're giving off. We look at this elemental balance of stuff that's in them, and all of those things together give us some indicators of their age. There's a very famous diagram, if you go read about it, called the HR diagram, the Hertzsprung-Russell diagram. Okay, so I told you that word main sequence. Okay, that's a statement about where stars fall on that diagram. And one of the things that we know is that stars throughout their lives move around that diagram. And so where they are in that diagram is an indicator of its age. And that's largely determined by their brightness and their color, or brightness and their temperature. But these other factors are kind of more refined qualities that we're trying to use to understand their evolution and their processes. There are stars that we think are close to the point where they might explode, but we have no way of knowing. I mean, we've never seen it happen, so we're guessing at this point. Yes, sir.
I'm curious about the total number of stars in the universe versus the total number of planets in the universe, because clearly that ratio has changed over time, right? So 400 million years after the Big Bang, there were just stars, no planets.
Yep.
Then second generation of stars started popping up, and they were forming planets. Now we're 14 or so billion years after the Big Bang. We don't really know the total number of planets, but there might be a time in the history of the universe where there are actually more planets than there are stars.
Right. So the early universe almost certainly doesn't have things you and I would call planets in it.
Right.
Because they're made out of heavy stuff. So you need to get through a generation of stars before. when we look at the Milky Way, so this is the only thing we have to go on right now. So the Milky Way is a modern galaxy. It's not an ancient galaxy, but the modern galaxy. It's clear that the fraction of stars with planets is high. And in particular, what's startling to us right now is that small stars, what we call dwarf stars, M-dwarf stars, have lots of planets around them, which was unexpected. And so what that means is that the statement you made is almost certainly true, which is if the smallest stars have planets on them, then because they dominate the universe, then almost certainly by number, not by mass, but by number, there's probably way more planets than there are anything else. Yeah.
Thanks.
Okay. Everyone good? John.
What's the best reasoning as to why the cosmic microwave background radiation was not even? Hence, we're here.
So if you look at the cosmic, so what John's asking about is this cosmic microwave background picture I showed you. It has a kind of structure in it. It has ripples. Right? So those ripples are differences between the amount of microwave light in one spot versus the spot next to it. Okay? But the difference here is exaggerated. Okay? The difference between one spot and the next spot is a difference of 1 part in 100,000 or so. Okay, so the microwave background, the statement about the microwave background is it's extraordinarily uniform.
Mm-hmm.
Okay, but these spots are connected somehow to the amount of stuff that we have today, the numbers of galaxies and their distribution. And exactly how that connection is made is a complicated story, but it's reasonably well understood, and it matches well with our expectations. There are still some uncertainties and things that we are arguing about, let's say, because we still don't know about things like dark energy, and we still don't know things about dark matter, and they change that story when we put it all together. But by and large, you'll hear people talk about lambda CDM cosmology, right? They're talking about how do you make the connections between the structure that you see in the cosmic microwave background and what we see the universe look like today, and those two things match very well.
Was there something fundamental in the instant of the Big Bang that gives you that randomness?
We would love to know the answer to that question. We do not know the answer to that. If we could detect gravitational waves from the Big Bang, we might be able to tell you something about that.
And
So we'll see.
Lisa may do that? At the edge.
Lisa's going to do everything. So. Wait, did I say that out loud?
By analog, if I took a bucket of beans,
Uh-huh.
threw them on the floor,
Yeah.
would they be evenly distributed, or would there be clusters?
So this is so that depends on how you throw them on the floor. Okay. Okay, but when I was first a professor, one of my students did a physics outreach project where she dropped 20,000 bouncy balls out of a helicopter. So just go to YouTube and search 20,000 bouncy balls helicopter, you'll find Lindsay's, and there's awesome video of it. But if you kind of uniformly drop, things will spread out uniformly. Okay? Then to answer your question, you ask the following question, which is, I'm going to ask, did these things spread themselves out evenly or not? And to answer that, you have to say, I'm going to take a hula hoop and lay it down and count how many beans are in the hula hoop.
Right.
And then I'm going to move it, and then I'm going to move it. And for a certain size hula hoop, you're going to get that they're perfectly even. But for a smaller hula hoop, it won't be, right? So the universe is granular on small scales, but uniform on large scales.
Okay.
In the same way an orange is smooth, but the wrinkles are not perfect smoothness, right? So it depends on what scale you're talking about. And there's interesting and important physical processes that govern on the small scales how things cluster or don't cluster. In the case of galaxies and structure in the universe, dark matter plays a huge role. Who's talking? Yes.
I know this is really dumb.
There are no dumb questions. Just
The
ask.
dark matter
Uh-huh.
and the cosmic.
Microwave
if
background.
The cosmic microwave background fills everything up, and you think dark matter might be out there filling everything up. How does that compute?
So the distinguishing characteristic of dark matter is it does not interact or generate light of any kind. And
So no
the microwaves are just light, so they do not interact with the dark matter. They're influenced by the gravity of the dark matter, but it doesn't get absorbed and re-radiated, or otherwise would be able to detect the dark matter by looking at microwaves.
So the microwaves are light.
The
So
microwave is a form of light, absolutely, yes.
Ah,
Okay.
and then there's dark matter.
And then there's dark matter, which we still don't know what it is. Yeah.
Thank you.
Okay, that's a good question.
Then there's dark energy.
And then there's dark energy, and that's a
Is
whole
that
other bucket of
different
weeds.
from
So,
dark matter?
I'm sorry to ask
you're
all
good.
these.
Keep asking.
Okay.
This is why I'm here.
Okay, you-
My flight's tomorrow at 6. Okay.
You need a
hope.
ride. You were saying that you all now believe that all these stars have planets, so that it's now up to
Yeah.
4,000.
4,000 that we've detected, yeah.
Whatever it was. Do any of these planets die? Can you see that happen? Because like we're a planet, and
So
if we're cooling down, is our planet cooling down and dying?
As soon as
or
the
is
sun
it-
dies, we're history.
that is a true
When it
statement.
goes to the red giant, we're toast.
Yeah. So the very first planet we discovered, the first planet in the modern era that we discovered. Actually, let me tell you about the first planet we discovered. So the first planets were discovered in 1994 by Alex Wolskin at Penn State. He discovered them around a neutron star. Okay? So a neutron star forms when a star explodes. And that explosion, the energies that we're talking about, should destroy the planetary system. So the question is, where did those planets come from? Okay, and what we think is the planets were destroyed in the supernova, and then the gravity gathered them back together and formed new planets around the neutron star. That's the current best guess.
There are free-floating planets, though, too.
There are also rogue planets. So I did a TEDx talk about Pluto. So if you go watch that TEDx talk, I talk about the rogue planets in there. But planets, what I showed you, them forming around the star, as the planetary system evolves, sometimes they interact with each other, and their gravitational interaction lets one loose, and it goes floating around out in the galaxy without a star. Okay, and we've seen many of these. They're called rogue planets. The biggest one's about the size of Neptune. Okay. The first planet we discovered in the modern era is around 51 Pegasi, which is a nearby star in Pegasus. You can see with your naked eye. It is Jupiter-sized, but it's closer to its star than Mercury is to our star. And so the star, 51 Pegasus, is slowly evaporating that planet, which means it will eventually die. It will be gone. It will be oblated, as we say. Okay? And we are confuddled by this, right? We don't know how to get Jupiters that close. We don't know how they survive as long as they do. This is the frontier of modern planetary astrophysics. So if you want to come back and get your PhD, we got some projects for you. We need to answer that question. So what we do is we simulate them on computers. We do billions of simulations. We set up different early solar systems and evolve them forward in time, trying to answer exactly these questions that you've asked. But I don't think we know the answers very well. Okay? Uh-huh.
Any other questions for
Do
Shane?
you have other TEDx talks?
I have 3 TEDx talks up, so yeah. I have one, the one about Pluto, that was my very first one. I have one about, kind of about star stuff. It's called, I can't remember what it's called. Anyways, feeling small in a big cosmos. It's about big numbers and us trying to understand the cosmos. And then the other one is about the fact that science is really hard, and if we can solve these hard problems, we can solve other hard problems. So,
So
Okay.
if there are no more questions, a couple of things then. If you would be so kind, I mean, some people left some plates and things behind. If you could be so kind as to help bus it so that the senior center is remains
Happy
happy
with
with us, that would be really appreciated. Sarah Godsey from Idaho State University will be here for the first Tuesday talk at the library. And the third Tuesday, so in 2 weeks' time, on the 19th, 2 weeks from last night, she'll be here. And she's going to talk basically about water in the West, about why ephemeral streams are critical to all of us. She's a good scientist, and that'll be a good talk. And then beyond that, I would like to ask you to just join me in thanking and saying many thanks to Shane here.